Hi there, this is a quick tutorial on our chi-square test Excel calculator, and I'm on the first tab, which is a chi-square test for a single group, also known as a goodness of fit test. Uh, See these things referred to differently in different texts. And so the problem says a researcher was interested in studying the phenomenon known as social distance, and that's the reluctance of people to associate with members of different ethnic and racial groups. She designed an experiment in which students enrolled in a lecture course and were asked to choose a discussion group just based on the name of the person running that section. So you can see Chang, Schultz, Goldberg, and Rodriguez all sort of suggest different ethnicities. And the students did sign up at a different rate or frequency, right? So Chang got 10 students, Schultz got 24, Goldberg 10, and Rodriguez 16. All right, so altogether there are 60 students. That's just the sum of this column. So to do this particular test, we have to start with looking at what the expected enrollments were. So if you have 60 students in 4 sections, what you need to do is take that overall sample size and divide by the number of groups there that we're looking at. So 60 divided by 4, and that's going to be 15. Okay, so if I click on that particular cell, we'll see the formula is C9, which is the overall sample size divided by 4, the number of groups. And that's what you've got down the line there. The next step is to subtract the expected value from the actual observed value, right? So you can see the formula in this case is B5 minus C5. So this 10 minus 15, which gives us minus 5. And then we have the same thing going on below that, so the exact same formula for the next row of data, and it's like that all the way down. The next step is to square these values. So we have the deviation of the observed and expected, and then we have the squared deviation. So it's just taking, in this case, this cell, D5, and then using our formula to square things. So this the caret sign and the number 2. And that's like that all the way down, right? So we're squaring all those values. And then the final step is you can see the formula is the square deviations divided by the expected values. So it's going to be this column, E, divided by this column, C. And we do that for each row of data. So you can see it's E5 divided by C5 for that row. And then same thing, E6 divided by C6. And then it stays like that all the way down. And then our chi-square score is just going to be the sum of that column. Right, so we're just taking the sum of all those individual rows. So our calculated chi-square score is an 8.8. So then now we need to know is if that is statistically significant. So we need to know what the critical value is for chi-square. And to do that, we assume an alpha of 0.05 for our. We have a chi-square distribution table here that we can see there's different levels of confidence here. Okay, so we're going to look at an alpha 0.05. Degrees of freedom is the number of groups minus 1. So there's 4 groups here, minus 1 is 3. So at 3 degrees of freedom at a 0.05 level in our chi-square table, you can see right there, 0.05 level, 3 degrees of freedom, we have 7.815 for our critical value. So 8.8 is larger than 7.85, so our statistical conclusion is, we reject the null of no difference. So that means substantively, look at this substantive conclusion, enrollments do vary by the name of the discussion group TA, which means we do have evidence for this theory of social distancing. So that's one of the applications of a goodness of fit test. And you can adapt this by copying it. Right? If you move or copy that, you can create a copy. And then once you create a copy, you can change the what this is for, that you can change the number of cases, right? Number of rows, uh, change the problem. These things, you just want to make sure that if you are adding rows, that the formulas are also going to be added to the new rows, and that ultimately you're calculating the correct chi-square. And then you'll also have to adjust the degrees of freedom. Let's say you add a row here, so now your degrees of freedom will be 4. You'll have to go back to the chi-square table and, for instance, look at a 0.05 level would be 9.48 for 4 degrees of freedom. Okay, so you just have to adjust critical values and so forth. Okay, now in this particular problem, the second tab, we have a 2 by 2 contingency table. So the problem is the following 2 by 2 crosstab, that's another name for a contingency table, represents whether politicians are Republican or Democrat, and whether they favor or oppose strict gun laws. So favor and oppose, Democrat and Republican, those are the frequencies, those are the totals. Okay, so how do we find an expected value based on a contingency table? So down here we have to create this table, which you'll see is similar. If you look at the one group test, it looks very similar, except instead of these being the groups, these are referring to different cells in the table. So we have the upper left, which is 26, right? That's the observed frequency. We have the upper right in the table, which is 5, and that's here. Lower left, which is 7, and lower right, which is 19. So those are our observed frequencies. Now, when you want to calculate the expected values from a contingency table, it's a little different than we saw in the one group test. It was simply just dividing sample size by the number of groups. Well, we don't do that when we have a crosstab. Instead, you can see we need to multiply the row total by the column total and then divide by the sample size. So for the upper left, you can see if I click on that formula, it highlights the relevant cells. So we're multiplying 33 by 31 and then divided by 57. So that's multiplying B6 by D4 and dividing by D6. Okay, and that gives us 17.94. We're doing the same thing for each of those, except adjusting for the proper row and column totals, and we're always dividing by the overall sample size, which is going to be in the same cell. Then we're going to take the sum of the expected values, which should total 57, the total sample size. And then, as we did before, the rest of this is the same as we did here. So we just look at the deviation between the observed and the expected. Right? So just subtracting the two cells, so B10 minus C10. Then we do that all the way down for this column, and then square those values. And you can see these values don't differ, right? So that's D10 squared, gives us 8.05. D11 squared, because we're squaring it and we lose the negative, right? So this one was below, this one was above. And then this column is the same as well. We take the squared deviation and divide by the expected value. So in this case, it's E10 divided by C10. And then we do that same thing for each row. And then, as before, we add together the different rows to give us our calculated chi-square value. And then we also find the degrees of freedom in a different way with a crosstab. It's the number of rows minus 1 times the number of columns minus 1. So we just have 2 rows and 2 columns. So 2 minus 1 is just 1. 1 times 1 is just going to be 1. So we have 1 degree of freedom at a 0.05 level. Go to our chi-square table. You see it's 3.84 is the critical value. Well, our calculated value is far larger than that, so we reject the null of no difference. So there are differences between Democrats and Republicans in terms of their favorability on gun control laws. Substantive conclusion is just that. Right? So we have our both our statistical conclusion and our substantive conclusions. This is a 2x4 table. So in this last example, we just have a bigger table. We have more columns, which means now we have an upper left, an upper middle left, upper middle right, and upper right. Whereas with the 2x2 table, we just had the upper left and the upper right. So now we had this middle, these two middle categories. And you can imagine it gets pretty hairy when we start adding more columns. Yeah. So this table gets longer. Uh, or rows, right? When we add rows, we also, instead of having upper and lower rows, we'd have, upper and middle and lower, etc. So once again, we're just taking the observed frequencies from the crosstab and bringing them into a single column, right? So we're starting with row 1 and then row 2, just kind of flattening those out. When you take a row and turn it into a column, you can actually do that if you just highlight it and copy it. You can also just come over here and you see this little thing here, it says transpose. It's another way you can take the values and put them in there, but I prefer to use cell references so that way I can reuse this. I can add in different values. Let's say I made that a 4. Right? It changes and updates everything correctly because it's looking at the cell reference, not the value in that cell. Right? Okay, so same as before, all the observed are here. And again, the expected are from the row and column totals being multiplied and divided by sample size. We're doing that for each row here. Again, calculating the deviation, calculating the squared deviation, and then looking at the squared deviations relative to the expected frequencies in this column to help us calculate our chi-square, and then the sum of all those columns. So for this particular example, we see the calculated chi-square is 3.2. The degrees of freedom, we have 2 rows, so 2 minus 1, and 4 columns, so 4 minus 1 is 3. Right, so 1 times 3 is 3. Go to our chi-square distribution. At a 0.05 level, 3 degrees of freedom, you see 7.81. We've seen that one before, I think. And you see 3.28 is smaller than that. So since the calculated value is smaller, we fail to reject the null hypothesis of no difference. So we do not have enough evidence to suggest that enrollments for this, sorry, this is a different, we don't have enough evidence that there is not a difference between candidate A and B. There we go. Sorry, you could tell I made this sheet from this one and I didn't update the conclusion. So you have to be careful with that when you're doing these types of calculations. All right, so that's it. Thank you.